Let's start our journey into machine learning with one of the most simple algorithms out there, linear regression. What is linear regression? Well, very simply, we're just fitting a line to a data set of observations. So in the context of machine learning, what we're doing is taking a bunch of data points and trying to mathematically fit a best fit line to those data points. So we're training this model based on the data points we're seeing, and our predictions that come out of this model will be made by the equation of that line. Okay? So we will use this line then to predict unobserved values, new data that the model's never seen before, just by applying the line equation there. So for example, in this image here on the corner, we might have a model that tries to predict height based on your weight. And we might have a bunch of data points that map different human beings, real measured people, of their weight versus their height. And we might see there is a linear relationship that can be fitted to that data. And once we have that line, we have an equation associated with that line. In this case, it might be 0.6 times weight plus 130.2. So if we have a new weight come in that we've never seen from a person that we've never seen before, we can just plug their weight into that equation and come out with a prediction of their height. So kind of the simplest machine learning model in the world at the end of the day. The term regression is a little bit confusing. I mean, we're not actually trying to go back in time or anything like that, but that's what linear regression means. We're just trying to fit a line to observed data and then use that line to predict unobserved data. How does it work? Well, generally speaking, it uses a mathematical technique called ordinary least squares. The idea is that it tries to minimize the squared error between each point and the line. So as we try different models of the line, we try to minimize the error between the actual observed data point and the distance to the line that we are trying to create to predict those data points. If you remember the slope-intercept equation of a line, it's y equals mx plus b, where the predicted y value is equal to some slope m times the x value plus some y offset that we call b. I mean, you should remember that from high school, hopefully. Now, the slope turns out to be the correlation between the two variables times the standard deviation in y divided by the standard deviation in x. You can prove this mathematically. And it's pretty cool how standard deviation ends up having this real mathematical meaning here. So we have this kind of vague statistical concept called standard deviation that measures, the deviation from the mean for a given set of data. And you can actually relate that to the slope of this line in linear regression quite directly. Math can be kind of a beautiful thing sometimes. And the intercept can be worked out to be the mean of y minus the slope times the mean of x. So mathematically, that's how ordinary least squares works. But the good news is you don't have to worry about that because Python will do all of that for you, at least through the packages that we use. So you don't have to code this up by hand. There are just packages you can use to do this for you. Anyway, getting into a little bit more depth as to what's going on under the hood, least squares is trying to minimize the sum of squared errors. So it looks at the error between your line and the actual point that it observes at each point. So for every point, it takes the actual value of that point, it takes the error between that and where the line equation says it should be, and just sums up all of those errors together across the training set. So if you think of this problem in terms of probabilities and probability distribution functions, you can actually describe this problem as maximizing the likelihood of the observed data being correct. So sometimes we call this process maximum likelihood estimation. Just, more fancy words for what we're trying to do here. And there is more than one way to do it. We don't have to use ordinary least squares. We can also use a technique called gradient descent. And in the field of AI and neural networks, it tends to be how we do things. The idea is that we basically iterate to find a line that best follows the contours defined by the data. So we're descending along the contours of our data set here and trying to find the minimum error values there as we go down those contours. Makes a little bit more sense when you're dealing with multi-dimensional data because then you can actually kind of visualize these contours a little bit better. But these same contours exist in 2 dimensions as well, so it's not limited to multi-dimensional data. It's just that in 2D data, ordinary least squares is often a more straightforward approach. Like I said, it is popular in neural networks because gradient descent is this iterative technique that really fits well with the concept of training a neural network as you feed it more and more data over time and propagate that error backward through the neural network. We'll get into that in more depth shortly. How do we measure the error exactly from our predicted model of a line versus the actual data that we have? Well, we use a metric called R squared. It's also known as the coefficient of determination. And what it measures is the fraction of the total variation in y that is captured by the model. So we want to measure how well does our model capture all the variance that actually exists within our data that we actually know the answers for. Mathematically, it looks like this. Pretty simple. It's just 1 minus the sum of the squared errors. So basically the error is the distance between each predicted point and where it actually is, over the sum of the squared variation from the mean. So that's not looking at the difference between the predicted value and the actual value. It's looking at the difference between the actual value and the mean of the data as a whole. Those are two different things, okay? And R squared is just 1 minus the ratio of those two things, the sum of squared errors over the sum of squared variation from the mean. And that way we get this measure of how well our model captures the actual variance in our data. R squared can range from 0 to 1, and the way to interpret it is 0 is bad, meaning that none of the variance in the data was captured, and 1 is good, meaning all of the variance in the data was captured. So let's dive into an exercise and actually see how linear regression works with some real data.